Continuing our discussion on multiple facility location problems, we have seen three varieties: set covering problem, partial set covering problem, and p-median problem. If you recall the objective of set covering problem, it was very simple: to ensure that all the nodes are covered by at least one facility. So the nodes can be served by at least one facility. If it is it is getting served by more than one facility, that's okay. In the partial set covering problem, we said no, we may not have enough budget to cover all the nodes, but partial set covering problem essentially said, can I maximize the number of nodes that I can actually cover? I know that I may not be able to fully cover the nodes, but can I maximize the number of nodes that I can cover, right? So the objective changed from minimizing the number of facilities that can help me cover the entire set to a new objective which wanted to maximize the number of nodes that I can actually cover. That was the partial set covering problem. Then we discussed the p-median problem. The p-median problem again has a different objective function. P-median problem tries to minimize the total weighted distance traveled by the customers to the facility, and we discussed whether the customers can be retail customers, can be retailer themselves, right? So essentially, people who use the facility, how do we minimize their weighted distance? And weight is essentially the population density, the customer density. And that also had a very strong budget constraint, saying that I can only have p number of medians, which is why the name of the optimization problem is actually a p median. Median essentially represents the facility. So that summation of yj to be less than or equal to p represents the budget constraint, saying that I only have enough money to have p number of facilities. Now, and we discussed that here, unlike set covering problems, we had a variable xij, and xij represented an assignment variable, right? Xij represented an assignment variable. This was that assignment variable, and here xij essentially meant that optimization problem gets to choose which node is assigned to which facility, because there is no aij here, but the optimization problem says that assign the nodes to the facility in such a way that the total weighted distance, this is the total weighted distance, gets minimized, right? That was the objective. And we saw the constraint, we saw this constraint, we saw this constraint, right? The objective of this session is to generalize the p-median problem now. In what way do we want to generalize? P-median problem is always going to have the budget constraint that defines the p-median problem. We can only have p number of facilities, and p is always going to be lesser than the total number of nodes that we have. So the trivial solution that was available to us in the set covering problem is no longer available. What was the trivial solution that was available in the set covering problem? In a set covering problem, we said the trivial solution is to have a facility at each node, right? But we don't have that kind of budget, right? So that constraint is going to remain. This constraint continues to be there, right? So if you are assigning a node to a facility, make sure that there is a facility, right? So this constraint guarantees that. So that constraint is not going to change in the generalized median problem. But let us change the objective function, right? Let us change the objective function of actually having a facility and running the facility, right? So there is going to be some fixed cost, and then there is going to be some variable cost of assigning the node to a particular facility. So one more change that we wish to bring in is, since we are changing the objective function, let us bring back aij, right? What was aij? Aij was always the feasibility parameter. What was feasibility parameter? Can node I be assigned to a facility at j? Can node I be assigned to a facility at j? P-median problem did not have aij. Remember, aij is a parameter. Aij is an input to the optimization problem. We are telling the optimization problem whether node I can be assigned to a facility at j if there is a facility at j, right? Okay, so let us get into the formulation of a generalized median problem, right? So generalized median problem, as I said, let us bring back aij. Aij is 1 if node I or vertex I can be assigned, right? Can be assigned to the median at vertex j, right? And this can be defined anyways, right? In the set covering problem, we said oh, anything less than or equal to 30 miles is a feasibility constraint, right? Or anything else, right? This can be defined in multiple ways. It can be in terms of distance, it can be in terms of time, it can be in the sense of other feasibility conditions, right? But now we are bringing back aij, and as we said, now our focus in the generalized median problem has shifted to cost minimization, not travel time minimization or travel distance minimization. P median problem has had an objective of minimizing the weighted distance. So what are the cost parameters? Let us say fi is the fixed cost of having a facility at j, and cij is the cost of serving the node I from j, right? So this kind of cost may be a typical assignment cost, right? What is the cost of assigning? What cost does the organization incur if the customers are traveling from node I to the facility at j, right? The organizations are incurring, not the customer is incurring, right? Or it's easy to explain. It's easy to explain in terms of, for example, e-commerce business. Let us say that I locate a warehouse at j. And what is the cost of serving the customer who is sitting at node I? I mean, for example, if you are in Mumbai, and let us say that your warehouse is located somewhere in Navi Mumbai, and what is the cost of serving the customer who is located in Andheri, for example, right? So that's the cost. So for a example like e-commerce, it's very easy to explain that here the organization is traveling, the representative of the organization travels from the warehouse and delivers the package to the customer's house. So that CIJ is very easily explainable, but this is, remember, the cost incurred by the organization when they are serving a customer located at I from a facility that is located at J. And using these Fi and Cij, let us modify our objective function. And now let us say that objective function is minimization of the total cost. So I have P facilities. So summation of all the P facilities cost. Fj Yj is the fixed cost of having the facility at J, right? Fixed cost of having the facility at J. So Yi indicates whether there is a facility at J. Fi is the cost of having the facility at J. And then this is the running cost, which is the serving cost or the assignment cost. Cij Xij indicates the cost of serving the customer located at J from a facility located at, sorry, I said it wrong. Cij is the cost of serving the facility, serving the customer located at I from a facility located at J. And Xij is the assignment variable, right? Xij is the assignment variable, which is the same variable that we had here, right? Now for generalized P median problem, we had Aij, which is the feasibility. So the original constraint of summation Xij equal to 1 has to change. Now I cannot say that I will assign the node to the facility. Now that has to depend on the feasibility Aij, and therefore this summation Xij equal to 1 has to change, and now it has to become Aij Xij equal to 1. I cannot simply assign the node to a facility, it has to be feasible, and Aij is the parameter that indicates feasibility. Okay, so that constraint has to be changed, and all the other constraints can remain same, which means that this constraint will remain same. What does this constraint say again? Let us recall. If you are assigning a node to a facility, you better have a facility at J, right? That's what this constraint says. And obviously you are saying that I can only have P number of facilities. I can't have a facility, I can't have a warehouse in each of the suburbs, right? That's what you are saying by this constraint. So this constraint remains the same, this constraint remains the same. This constraint is slightly modified to indicate feasibility. And the most importantly, in the generalized P median problem, we have changed the objective function from minimizing the total weighted distance to minimizing the total cost of running and serving from the facility. Okay, so fairly straightforward, fairly simple. Once you have understood P median problem, generalized P median problem is just a generalization of that. Okay. Now let us look at one final formulation in the multiple facility location problem, which is called maximal covering problem. Okay, so I will give you a very representative example of a maximal covering problem. What is a maximal covering problem? This is a generalization of a set covering problem. So set covering problem, if you recall, was to minimize the total number of facilities required to cover the set. Then we looked at partial set covering problem and then said some budgetary constraints may not allow us to have multiple facilities. But given the fact that I have so many facilities, what is the maximum that I can do? Right? What is the maximum that I can do? Now I am not talking about the objective of set covering problem, partial set covering problem. The objective of partial set covering problem was to maximize the number of nodes covered with a minimum number of, with a given number of facilities, with a limited number of facilities. So objective was maximization of the number of nodes covered. Right. Now let us think about an example. Let us say that I will draw a shortish network. Let us say that this network is available, right? And let us say that node 1, node 2, node 3, node 4, and there was a AIJ which told us the feasibility, people should not be traveling more than 20 miles, the people should not be traveling more than 30 miles, people should not be traveling more than whatever, right? Some constraint, right? So now let us say that if I have a facility at 4, and my minimization and my feasibility condition is they cannot be traveling more than 30 miles. So if I have a facility at 4, it only covers node 2. Right? If I have a facility at 2, it covers node 1, node 4 and node 3. All 3 nodes are covered. Right? If I decide to have a facility at 1, it covers node 2, but that's all. Right? So you have all these constraints. So let me put this as 40. And let us say that I am trying to decide the facility at 2. Trying to have the facility at 2. Now what this will do is, this is a rather poor example, but that's okay. Helps me explain. So now sometimes what happens is I don't want to cover the nodes. I'm not in the realm of partial set covering problem where my objective is to maximize the number of nodes required to cover everything, right? So but the objective is, let us say what was not covered in the set covering problem was, let us say that the demand here is 100, the demand here is 400, the demand here is 20, right, and the demand here is 45. Now, if I have a facility at 2, it will surely cover node 1, no problem. It will surely cover node 3, no problem. Obviously, it will cover node 2. But look at the total customers served. How many customers are you serving? You are serving 20 plus 45 plus 100. Right? Only 165 customers are served. Now, look at node 4. If you locate a facility at node 4, let us say that you can have only one facility. If you locate that facility at 2, you are covering 3 nodes, which is what the partial set covering problem would have done. Now we don't want to do that. What we want to do is, we want to locate a facility at 4 because it serves 400 customers. Obviously, it doesn't serve any one of the nodes, right? It doesn't serve node 1, it doesn't serve node 2, it doesn't serve node 3, because all the distances are more than 30 miles. But having a facility at node 4 itself is good enough for me because it maximizes the number of customers that I am able to serve, given the fact that I can only have one facility. So rather than locating that facility at 1 or 2 or 3, I would much rather locate the facility at 4. So now you understand the difference? The difference between set covering problem and maximal covering problem is, now I am trying to maximize the serviced demand. I am not trying to maximize the number of nodes covered, right? So that is the difference between a partial set covering problem and a maximal covering problem, right? Obviously, everything is done in the context of facility location. Okay. So in the P median problem, the objective was again very different. Objective was to minimize the total weighted distance, given the fact that there was a very severe constraint on how many facilities I can actually open. So P median problem was again different. Okay, so this is some kind of a generalization for partial set covering problem. I am now trying to maximize the serviced demand, total serviced demand. Okay, so in addition to this serviced population, there may be some additional constraints. For example, think about locating facilities for fire station. Right now, every city requires fire station. What are the constraints for the fire station? Obviously, I want to be able to reach maximum as much population as I can reach, so that in case of some emergency, the fire station can serve the community. No, absolutely. So that is the service population. I want to be able to reach as much population as I can reach, maximize that population that I can reach. Additionally, I may have some other constraints. For example, if I'm locating a facility like fire station, I want to have time constraints. I want to locate a facility in such a way that I'm able to reach maximum number of people within half an hour, or maximum number of people within 45 minutes. So not only do I have to say that my objective is to reach maximum population, as much population as I can reach, I should be able to say that I want to reach them within some specified time, right? So for example, it is desirable to locate facilities in order to maximize the population, yes, but that can also be served within 5 minutes or 15 minutes or 20 minutes, right? And then there can be other constraints, which is the additional constraint, saying that, well, I want to maximize the population that I'm able to reach within 5 minutes, but entire population should be reached within 10 minutes, right? So 5 minutes, 10 minutes may be very tight. You can think of them as half an hour, 45 minutes, but you can see that there is a layered constraint here. First is maximize the population that can be reached within 5 minutes. This is one constraint. Second constraint is entire population should be served within 10 minutes, right? So going back to my smallish example here, right? If I want to impose those two constraints in terms of time, right, in terms of distance, I can say that maximum nodes should be within 30 miles, but all the nodes should be within 40 miles, right? So layered constraint. Maximum number of nodes should be within 30 miles, and then I can say not nodes, right? Maximum number of population that should be within 30 miles, not nodes. Nodes would take us to partial set covering problem. So maximum number of population should be reached within 30 miles. All the population should be reached within 40 miles, right? So all the population. So there are two constraints now. Okay. So the secondary constraint, which is the 10-minute constraint, is called mandatory closeness constraint. Okay, so that's called mandatory closeness constraint. So that says that mandatorily I have to impose this closeness constraint, that I have to be close enough to population that entire population can be reached within 10 minutes. Entire population can be reached within 40 miles, right? So that's how we want to impose the conditions here, which were not there in any one of the previous formulations. Okay. So let us get into the mathematical formulation. Let us say that I is the index of all the possible nodes, all the possible demand locations. Each of the demand location has a density of pi, right? Where that's what I told you. Here the density matters. Here there are 400 users. Here there are 100 users. Here there are 45 users. Here there are 20 users. That matters, and that is indicated by that parameter pi. And j indicates the set of all the possible sites, right? And they may be same, they may not be same, right? M may be there is a possibility that m may be lesser than n. There are some sites, there are some demand centers which are not good sites, right? So all that is possible. But what is definitely true is I can only have k number of sites out of these m, right? So how many facilities can I have? There are m potential sites, but out of these m potential sites, I am going to open facilities only at k number of these locations. Let us say that the maximum allowable response time is r, which is what we were saying, right? Maximum allowable, which is that 10 minutes, maximum allowable response time, or the distance. It may be specified in terms of distance, 40 miles or 10 minutes, or think about fire tenders, right? Think about fire tenders, emergency services or ambulance services, right? There you would want to impose these kind of constraints. So Let us say that if this k is very tight, if the number of facilities I can actually have is very tight, I know that I may not be able to serve all the customers within 5 minutes, right? So I want to maximize the population. I want to maximize the population that I'm able to reach within 5 minutes, right? So my objective is to maximize that population that I'm able to reach within that time, and that additional constraint of r, that everybody has to be reached within 10 minutes, right? So let Tij be the time or distance from the jth site to the ith demand center, and then I'm going to impose very strong feasibility constraint using a parameter Aij. Aij has always been our feasibility parameter. Aij will be 1 if Tij is less than r. If Tij is less than r. Okay. So we can have this as 5 minutes first, and then we can expand that to 10 minutes. Let us impose this as 5 minutes. Okay. So this tells me whether node I can be served by a facility at j, because that will be governed by whether the distance is less than 30 miles or distance is or the time is less than 5 minutes, right? That will dictate the feasibility parameter, which is Aij, will be 1 or 0. So what will be the formulation? Yj remains Yj, our earlier decision variable. Yj is 1 if we decide to build a facility at j, and therefore our formulation changes, right? What do we want to maximize? We want to maximize the population that is reached, right? And Aij indicates the feasibility, right? Aij indicates the feasibility. So and this is maximized over j, right? This is maximized over j. So so how will that work out? How will this constraint look like? So let us say that I is 1 first. For I equal to 1, how will these variables look like inside? So it will be A1j, P1, right, and Yj. And then this is true for all j's, right? So summation. So what is this? So it will be ai, right? A1j. So j is 1. Let us say P1 Y1, or A12 P1 Y2, or A13 P1 Y3, and so on, right? Now, if you decide to have a facility at 1, can it serve node 1? If you decide to have a facility at 2, can it serve node 1? If you decide to have a facility at 3, can it serve node 1? So this A11, A12, A13 need not always be equal to 1. So what are you going to do? You are going to pick the maximum out of these values. Essentially, maximum will be same because this is P1, this is P1, this is P1. Anyway, Aij is a 1, 0 variable, Yj is a 1, 0 variable. So you are going to get only P1, P1, P1 or 0. Right? So you are going to pick the maximum so that that node is covered, or that population is covered. P1 population is covered. And do that for the second node. Say I equal to 2. Do the same thing. So you want to pick maximum of A21 P2 Y1, A22 P2 Y2, A23 P2 Y3, and so on. Right. So if you decide to have a facility at 1, does it serve node 2? If you decide to have a facility at 2, does it serve node 2? If you decide to have a facility at 3, does it serve node 2? Right. So Y2 is a decision, but once you take a decision, can it serve that particular node? Right. Will decide whether this guy is 1 or this guy is P2. This guy is 0 or this guy is P2. And you are going to pick the maximum, so that you are obviously trying to pick P2, so that the population at that node is I2, population at the second node is also covered, right? So this becomes our objective. Our objective is to maximize the population that can be reached within that specified time, right? 5 minutes or 30 miles, right? So that is the first set of constraint. The second constraint is to ensure that yeah. So Pi is if Pi is 1, right? If Pi is 1, if the entire go back. If demand is same at all locations, which is 1, then essentially your maximal covering problem behaves much like a partial set covering problem, right? That's always going to happen. So when P is 1, so the game is essentially different because there are different demand densities. There are different demand densities, and I want to serve as much people as many people as I can. Otherwise, it's just a set covering problem, a partial set covering problem, right? So the mandatory closeness constraint. Now let us come to the second set of constraints. Mandatory closeness constraint says that demand centers cannot be more than T minutes away from the facility that is open, right? And obviously this T is more than R. This T is your 10 minutes. Your earlier R was 5 minutes, right? So entire population has to be reached within 10 minutes. You want to maximize the population that can be reached within 5 minutes, but you want to ensure that the entire population can be reached within 10 minutes. You have to have now another variable, another parameter, right? So to code this mandatory closeness constraint, we have to have a parameter. Let us say Dij, right? Dij is a parameter. It's a parameter. It's a 1-0 parameter. If your travel time is less than 10 minutes, then it is 1. Otherwise, it is 0. And then you will add a constraint that this Dij Yj has to be greater than or equal to 1. Right. So how do you open the facilities? You open the facilities such that your distance is less than 10 minutes for all the nodes. Right. Here you are not saying I will maximize the number of people that I am able to reach. Here I am saying that mandatorily, everybody has to be within the span of 10 minutes. Right. Within the span of 40 miles. Doesn't matter whether you say that in terms of time or distance. Right. So as I was telling you, the first constraint is the inner constraint. Right. First constraint is the inner constraint. I think I said it wrong. And the second constraint is the outer constraint. Right. So 40 and 30. 30 and 40. Right. So 30 and 40. 30 and 40. So that's how you formulate a maximal covering problem. A maximal covering problem maximizes the population that can be reached rather than simply covering the node. So it's a covering problem, but it's not covering only the node. It is actually covering the underlying population at each one of the nodes. Okay, so we have seen various formulations, and by no means this is an exhaustive list of all the optimization formulations you can have for facility locations, but we have given you a flavor of single facility location and multiple facility location. Obviously now we will have tutorials on how to formulate that problem, how to solve those problems. In terms of optimization, if you had noticed, all the formulations were integer type, right? Integer type, because your decision variable was integer. Right? So in terms of complexity, these problems are harder problems to solve compared to the LP problems that we had seen in some of the other courses. Okay, so with that, let me close the discussion on facility location, and we will take up next topic of supply chains in the subsequent sections.